Also, we have this weird-looking robot, and I think we animated this as well. Serves the purpose of combining all the transformation in one place, so that we can, for example, let me show you over here. How do I pause this? Alright, okay. So if you look at this figure only, you'd see that this 3D mesh is built out of a lot of vertices. Not a whole lot, we got only 64 of them, but you can imagine that we can bring in subdivision, subsurface, or you can also increase the geometry a bit by introducing loop cuts to, let's say, to bring in some deformity in it, in the shape itself. So the number of vertices will increase, and that would mean that when you rotate something, let's say when you rotate this, it will be affecting all the vertices on this part. Okay. But at the same time, when you rotate something else, it's going to affect that part as well if it is connected to it. Okay. Now, for a simple animation like that, you can imagine that we had a cylinder right here, right at the origin, but that thing actually got shifted over here and also got rotated. So that means that we already have a translation and in a rotation of some sort taking into account in multiple places. And there can be multiple rotations. There can be a rotation on itself. There can be a rotation over here as well. Okay. So let us talk about another example, and I think it's probably better to use another setup. So the example that we were talking about, a solar system over here, let's say we got a sun like this, and we have an Earth right in the middle. Okay, it doesn't look like so, but now it does probably. So let's say the outer one is our sun and the inner one is our Earth. So the first affine transformation that we apply over here is a scaling, right? And then we see that the Earth needs to rotate on its own axis, and I'm not talking about the 23.5 degree inclination that we have, rather let us just rotate it like so. Alright, so it's going to rotate it on its own axis, so there is a rotation like that right at the start. And then what happens over here is that it gets shifted like so, and then it rotates about the origin. So there is a rotation that happens on its own axis, and then it orbits around the sun like this. Okay, so what are the things we applied over here already? We applied a scaling to start with, then a rotation for its own axis, then a translation, and then a rotation that would orbit it around the sun. Now if you bring in some more stuff into the mix, like if you bring in the moon that revolves around the Earth itself, then that would mean that the moon will have some extra rotation and also translation. Well, you have to translate from the Earth itself, then it rotates around the Earth like this. That again brings another level of complexity to the picture. Now, why is this important? Because as you can see already that the Earth that we have over here is made out of a lot of vertices. And, well, not a whole lot. We got 964 vertices for this guy over here. But that would also mean that whatever transformation that you apply needs to be applied to all 964 of them in one go. Okay? So let us try to simplify matters and try to get the idea why we are going to do things a bit differently than what you did in coordinate geometry. Now we already set up our formula for affine transformations in our last class. And let me see if I saved that. Actually I did. So we got the scaling, translation and rotate. We got formulas set up for all these things, but the formulas are quite different in terms of how they work. Like the scaling was, it's a multiplication. In translation, okay, in translation you see that it's an addition, and in rotate it's multiplication, subtraction and addition all in one place. Okay, so there is no common format for these things. So the example that we're trying to build over here, that the earth moves around the sun, it rotates on its own axis like so, and also orbits around the sun. So let us see what happens over here. For each point on the earth, let's say PE is a point on the earth, it can be any point on the surface of the earth. Okay. What do we have to do? Initially we have to scale this by a certain amount. After scaling, what was it that we did? We rotated that, okay, to get its own rotation on the axis that it has. Then we translated that, and then we rotate it again to get the final location of a point on the surface of the earth. Can we say this? Yep, sure. So let us go back to how things were before. We have the same size for the sun and the earth, but that's not going to work because the earth is supposed to be much smaller than the sun itself. Okay, so initially it was like radius 1, but now we want to make it smaller. That means that we want to scale it down. So that's the first thing. You scale it down to whatever size it is. If the radius of the sun is 1 unit, then the radius of the earth needs to be much smaller than that. So whatever it is, you scale it down based on that. And after that, you need to ensure that you have the rotation around its own axis, so it's going to rotate on its own. Okay, so that's a rotation right there. First of all, we got the scaling, and then we have a rotation. Then we need to shift it to one side like this, and then let it orbit. So the shifting means that we're going to translate on whatever axis it is, X, Y, or Z, depending on how you have set it up. And after that, we are going to rotate it around the sun like so. Is that clear? And if you want to show the vortex-like effect that I showed you in a video, maybe the sun will move along some particular line and the earth will be moving around as well. So that will create that vortex shape, and then we'll see that over here it's going to rotate like this, and it will also move along with the sun like so. All right. So everything combined, I mean, I'm not talking about the vortex right now, but this PE can be any point on the surface of the earth. As you can see that there are many vertices on the this sphere, and it's left as flat shaded, but it already has 964 vertices. So PE can be any one of those vertices, any one of those 964 vertices. It can be much more, but that's what it is, that we have a lot of vertices over here. We need to scale each and every one of them. We need to rotate them. We need to translate them. We need to rotate them again. So altogether, that would bring us a very simple animation where we see that the Earth moves on its own axis and also orbits around the Sun. That's a very simple scenario that we got over here. Okay. Now the problem that we face right now is that whatever point it is, okay, whatever point you have on the surface of the Earth, let us just take one example. Okay. Say we got a very simple UV sphere, and on this UV sphere there should be a point right here which is 100. Let me look this up. Yes, 100 is a point on this sphere. See? Right over here we got a point. So we can represent this in this format. 100. And then we are scaling this down. Right? So the first operation that we perform over here, if it is going to be a scale operation, let us say that we scale it by half. Okay, so what's going to happen there? This PE, whatever point on Earth we have to scale it by a factor of 0.5. That means that the first transformation will bring us the values half, 0, 0, and that we got using our transformation formula that we derived over here. Okay. So internally what's going to happen is that you have x prime, y prime, and z prime. For each and every one of these, you have to multiply with half, and then write down whatever coordinate that you had initially, which was 1, 0, and 0. Right? And once you have that, then you go for this rotation, and then you have to apply some other algorithm. So let us imagine that we're going to go with rotate on the z-axis by some 30 degrees. Okay, so what's going to happen? We are going to take this formula and then apply that on the result that you got from here. Is that clear? PE double prime after the application of the rotation is going to be, I'm not going to calculate this, but we can imagine how we're going to calculate this. We have the original point. X is half, y is 0, and z is 0. So we have this formula, x cos theta minus y sin theta, and y prime is equal to x sin theta plus y cos theta, and z prime is just what it was. So what you can see over here, that for each of these applications we have to go in a series, right? First of all, you apply this scale, then you apply the rotation, then you apply the translate, and then you go for the rotation again. So all these things are very much dependent. I mean, if you don't do the scaling first, you cannot apply the scaling, the rotation. Definitely you cannot apply the translate, or you cannot apply this rotate again. Why so? Because this formula, as we have developed over here, is internally dependent on the previous values of x and y. And understanding this part is very much crucial. So what it really means is that since we got 964 such PE, we have to take each of them individually and then carry out 4 different operations over here. we have to scale each one of them, we have to rotate them, we have to translate them, and we have to rotate them again. Now, there can be a lot more such operations. This is a very much simplified example. Over here we have only 4 operations, but in reality there can be a very long chain over here. So you can say that there can be, let's say, 100 such operations that happens on a particular vertex. And that would mean that all the vertices that are there on the same mesh, they will have to have the same set of transformation on them. That would mean that you have like 1,000 transformation on them as well. So this is a very bad example right here, that for each and every point that you have to carry out 4 different operations like this. What if we come up with a different construction in some sort, and we say that PE will be some operation over here, and the operation, noting it with a label M for a particular reason. If we could do the same thing in this format, then wouldn't that be simpler? Because this means that you just apply one operation on this thing. And what it also means that we can somehow pre-compute this part. So all these 4 operations, or 1,000 operations, or whatever many operations that you have, all these affine transformations, if you can combine them somehow to come up with a single operation, that would speed up the whole process quite a bit. We cannot do this right now because everything is dependent on one another. The first thing needs to happen over here, then this one, then comes this one, and then comes this one. If this part somehow can be pre-computed without depending on this thing at all, then we can simplify the process. Okay. Right now this is not possible because all the operations, they depend on each other, and they are also different kind of operations. So we need to think about a totally different model where this doesn't happen at all. Is the problem clear? Why things are slow now and what we possibly need to do? Let's set it 30. Yes. So in order to take out the dependencies and everything, we need to come up with a different formulation, and that's where we see that the matrices will come into rescue, because what we're going to invent over here, that we will have a separate matrix for scaling, a separate one for rotate, a separate one for translate, and also a separate one for this rotation. So if you combine them, what we'd have is 4 matrices one after another, and we can multiply them ahead of time. You do 4 matrix, 3 multiplication. You do multiplications like this to come up with a single matrix, and in the end what we're going to do is we are going to multiply the point with this one matrix that we got. So as a result, everything will be much more simplified. Okay. Let us look at the most simple example for scaling. Scaling can be done as matrix multiplication. If you remember the formula that we had, let me copy paste. Why this again? Okay, so this is the formula that we wrote for scaling. Okay, and we're going to convert that into a matrix representation. The way this works is that we will first of all have to represent the point itself, and that we're going to do as a column vector or a matrix with only one column. Okay, so let us say that this is our point P, and that's the matrix. It's going to be whatever coordinates that you're going to throw in and add it. Now if you look at this example, 1, 0, 0, we have x, y, and z. We can just plug it in like so. Okay. But in general terms, this is going to be x, y, and z values, one after another in this column. Now we need to make sure that we get the same matrix, well not the same matrix, a matrix of the same dimension as output, because we're going to chain them one after another. So from P we will get another matrix. It's going to be a column vector. It's going to be P prime, and over here we will have x prime, y prime, and z prime. Is that clear? And there will be some matrix sitting right here. And that's going to be our scaling matrix. Okay? Now I need to write down one thing over here, and I need you guys to realize this. This is a 3-row, 1-column matrix, and the output that we want over here is a 3-row, 1-column matrix. So my question over here is, what's going to be the dimension of this matrix S? 1 into 3? Okay, so let us try that out. Now I realize why you say 1/3. Because the number of columns over here should match the number of rows. That's how matrix multiplication is defined. However, you should also remember that once you do the product, the dimension of the resultant matrix is going to be the number of rows over here and the number of columns over here. So if you do the multiplication like this, you'll end up with a matrix that has size 1/1. So this is not going to work. If you're saying that we will have a 1/3 matrix over here, then after multiplication, you will have a matrix that is of size 1/1. But that's not what we want. We want a matrix that's of size 3/1. So that tells us that this is not the way. You need a 3/3 matrix over here. In that way, the number of columns over here matches the number of rows over here on the second matrix, and the dimension of the output of matrix is going to be the number of rows on the first matrix and the number of columns on the second matrix. Okay. So that's the first thing to notice, that the matrix we need over here as is will be a 3/3 matrix. Okay? And now we need to make sure that our formula is exactly the same thing we had for scaling, that x prime is equal to x into sx, y prime is equal to y into sy, and z prime is equal to z into sz. Okay. So whatever you do in terms of matrix multiplication, you need to make sure that this is the output. And that's the reason I ask you guys to look at matrix multiplication before you come to this class today. And that's a very bad color choice. All right. Okay, so the way matrix multiplication works is that you have to pick a row over here in the first matrix and pick a column over here in the second matrix. This entry right here will be multiplied with this guy. This one over here will be multiplied with this, and the third one over here will be multiplied with this, and finally you're going to add these three multiplications together to get one entry in the output matrix, and the entry, I lost my cursor, okay, the entry is going to be x prime. Okay, so help me out, what are the three numbers you want over here so that you get x prime equal to x into sx? Okay, let me start the process, all right? Let us say that we have the numbers 1, 2, and 3. Let us carry out the multiplication and see what we have over here. If you have 1, 2, and 3, what you get over here is x prime equal to 1x plus 2y plus 3z. But what we really want is x prime equal to sx times x. And how many y's do we want over here? How many y's do you see? No y's, that means 0 y's. This first line, x prime equal to x into sx, is there any y in here? So that means that we want 0 y's. How many z's? 0 z. That kind of gives you the answer already. So what should we put in over here? 1, 0, 0. That's not right. 1, 0, 0 will give you x prime equal to x only. Yeah, you're going to get this. But we want sx over here. Is that clear to everyone? That sx will be multiplied with x, 0 will be multiplied with y, 0 will be multiplied with z. If you understand this part, the rest should be pretty simple. What should be the entry for y prime? 0 sy and 0 0 sz. So let us look at one of these, all right, just to make sure that everyone is on the same line. This 0 gets multiplied with x. We're going to calculate z prime. This 0 is going to be multiplied with y, and this sz is going to be multiplied with z. So we get z prime equal to 0x, 0y plus sz z, which is what we have. Okay? So this is how we can come up with a matrix, a 3 by 3 matrix that actually takes care of the scaling. Is that thing clear? Okay. Now let us look at another one of these. So as you can imagine that what we are trying to do here, that we are going to reduce all these 4 operations into a single operation. That's the primary target. But in order to do that, we need to make sure that we multiply all these things together into this form. Because previously we are going to do this scaling only on one vertex, then we are going to take the result of it and do the, well, this will happen first, and then we do this, and then we do this, and finally we do this one. So there is a lot of dependency all around. That's something we want to avoid. Now, with this scaling task, things will be much better let us look at the rotate formula, and I'm going to copy this again. We have a rotation formula for z rotation of theta degrees, or whatever unit you're going to call it. We have that. So this is for rotation, and let me write it down. Let us be consistent over here. So this is rotate. Okay, and we got a formula for this. Now we have a very similar setup down here. Okay, I think I need to move things up a bit. I ran out of room. And I need to copy the last line also. Okay, so that's that. Now we have a very similar setup here. We have some point P. All right, let me copy this part. All right, so we have something very similar. We have a point P. We're going to put in a rotation matrix about the z-axis for some angle theta unit. All right. So these entries over here in the middle, it will obviously change, right? We're not going to scale. We're going to rotate over here. That's why they need to change. And over here, what you need to make sure that x prime ends up as x cos theta minus y sin theta. There will be no z entries. And let me make some room for that. Okay, so this is the rotation formula. We're going to need some room. We will write it as 3 entries over here, and the entries that we write down, they're going to be multiplied and then added up all together to form x prime. So if you understood the previous example, help me out with the entries over here. Cos theta minus sin theta and 0. Okay, so for the rest of you, do you understand why we write down cos theta minus sin theta and 0? Because the way matrix multiplication works is that you have to take this first matrix, log this row, and use it with this column. So x will be multiplied with cos theta, y will be multiplied with minus sin theta, and z over here will be multiplied with 0. So you add up all these things. What do we get? X cos theta minus y sin theta, and there is no z. And that's why this is exactly this formula for x prime at least. Now if you want to do it for y prime, sin theta, cos theta, and 0. Sin theta and cos theta and 0. Alright, so let me try it again. So sin theta cos theta and 0. And what about z prime? 0, 0, 1. So this is much simpler then. Okay, so we wrote down formula for 2 things. We wrote down a formula for scale. Well, let me be consistent over here. Since I wrote rotate, this should be scale or rotation over here. Now, since we have the matrix forms, we got one matrix S, we got another matrix RZ theta. Okay, can we then come back and solve the same problem? Let us just take a simplified look at this. We got a point on the earth, P, we have some scaling measure and we have a rotation. Let us forget about the translate and rotate for now. Okay, we will come back and look at it, but let us at least try this thing as it is. So what we are given right now is P is equal to a point on the surface of the earth, and this point is 1, 0, 0, like we see over here. This is 1, 0, 0, but it can be any other point, like it can also be 0.693, 0.138, 0.707. It can be that point as well. So PE for now is nothing but a representative point, and for simplicity, let us just take 1, 0, 0. Okay? Alright, so what's the next thing we're going to apply over here? We need to understand what sort of scale we're going to do. The scale will be equal scale on all sides. So this is going to be, to keep things simple again, half, half, and half. We will just say that the earth is half the size of the sun, which is totally untrue, but it doesn't matter. It's just a made-up example. And we will also apply a rotation, okay, of, let's say, 30 degrees. All right, so if you learn how to do it in coordinate geometry, this is a very simple problem. You do the scale operation first, then you do the rotate. It's just that we don't want to do it like that over here, and for a very good reason. But let us just set up the matrices, because we're not going to do it in a coordinate geometry style anymore. So if you're going to set up the matrices, what we have over here is 1, 0, 0 as the point on the earth, and then we need a scaling matrix, which is half, 0, 0, 0, half, 0, and 0, 0, half. How do I write this? Because that's what it is, right? Sx 0, 0, 0, sy 0, and 0, 0, sz. Okay? Now, for the second part, let me write down some labels. This is going to be scaled by half. So S half is the matrix over here, and over here we have Rz theta, which is cos theta minus sin theta, right? So we have cos 30. Let me write it down. We'll do it in 2 steps, no big deal. Cos 30 minus sin 30 and this one is 0, right? And this over here is sin 30 and cos 30. Sin 30, cos 30, 0. So sin 30 cos 30, not 36, and 0, and finally this is going to be 0, 0, 1. Is that clear? And this is our R, I hate that. This is our RZ, 30 degrees. I'm going to make some room over here. Okay. Alright, so that's that. And this will give us the final point PE prime, and that's going to be our X prime, Y prime, and Z prime. Is the problem clear? Okay. So let us do this step again, just to write down the values. In the next step, we will plug in the values for cos 30, sin 30, and everything else. This one right here is root 3 by 2, I think. So this guy over here has to be the same. And this one is minus half. And this one is half. Is this thing clear? So we just plugged in the values for sin theta, cos theta. I mean, you can definitely use your calculator over here. Right. So put the values in, and then we can carry out the multiplication. We can multiply all three matrices together to come up with one result. But I want to do it in two steps. See, if you went coordinate geometry style, what you could do is you could multiply these two vertices, these two matrices first, and then the result with this left one. But I want to go from left to right now. There is a particular advantage to that. How do you multiply two 3 by 3 matrices? And what's going to be the output? A 3 by 3 matrices, right? So for the first entry over here, in row 1, column 1, to get that, you have to multiply all these three numbers with the corresponding three numbers over here, right? So let me highlight the row and the column. So that's like root 3 by 4. And then what? This is 0 and this is 0, right? So add them all up. And what do you get? Root 3 by 4. Is that clear? Because we're going to take the multiplication and then we have to add them up. So let us look at the second one. For the second entry of this column, so this was the first entry done, and the second entry is going to be this row multiplied by the second column. So this one becomes 0, this is what? Minus 1 by 4. And finally we got a 0 over here as well, right? 0 times 0 is 0. So if you add three numbers together, this is how much? Minus 1 by 4. So this is done again. I will waste some time, but I think it's important that we do so because this needs to be really clear. Now for the last one, these two entries will be 0, and the final one, again, is going to be 0. So this is a very simple one. We write a 0 over here. Help me out with the second row. So for the second row, we pick this row and the first column, right? 1 by 4 plus 0 plus 0. Is that right? This will be 0 and this will be 0, obviously. So right here, this is going to be 1 by 4. And let us do it for the second entry. The second entry goes right here. This will be 0, and this one, root 3 by 4. And finally, we have a 0, so add them all together, that's what you get. For the last entry of the same row, what do we get? 0, 0, 0. Okay, let me save this file because I'm going to lose it otherwise. Let me know if you can't follow or if you don't understand something, let me know right away. For the last row, for the first column, what do we get? 0, 0, and also 0. 1 times 0, that's 0. So this is going to be 0. And for the second entry, we take the second column. What did we get? 0 times 0, 0 times half, and 1 times 0, which results in 0. And the final one, right here, is this guy multiplied by this. So what do we get? Half. 0 times 0 is 0, 0 times 0 is 0, 1 times half is half. So this is the matrix that I'm talking about right over here, that we have a matrix just like this. Now the beauty of this thing, let me just wrap it up. We got a point on Earth, that's PE, that's going to be 1, 0, 0, right? We write it down like this, and this is our matrix M. And to carry out the final computation, let us just do this once over here. This is going to be a 3 by 1 matrix, right? 3 by 3 multiplied by a 3 by 1 gives you a 3 by 1 matrix. So over here, what happens is that you take this one, multiply it with 1, this with 0, this with 0. So that's actually root 3 by 4. And this guy gets multiplied with 1, this with 0, this with 0. So we have 1 by 4, this multiplied with 0, this multiplied with 0, and half multiplied with 0 gives you how much? 0. So let us just wrap this off, alright? I'm going to use the calculator because I want to match it with whatever output we get from Blender. I want to see if I got the right answer. Alright, so right now this is going to be, I need a calculator here. Root 3 is equal to 1.732 divided by 4 makes it 0.433. 1 by 4, I know that already. This is 0.25, right? I'm just skipping 3 digits at the dot. It's not a good practice, but it will serve the purpose for now. So that's our output, alright? Let us look at Blender. Let us apply the same thing on this vertex. Okay, and I need to track this thing. So let me do it slightly differently. I will put a color to it so that I can track this guy better. Okay, so remember that we're actually tracking the bottom left corner point of this face. Okay, right, so this is the face and we're going to track this guy. What are the things we're doing? We take this object, we scale it by 0.5 first, and then we rotate it around. Do I have the screencast on? Yeah, no I do. So rotate, Z rotation 30 degrees. And let's see that yes, the point has indeed moved, right? It's not in the original location anymore. So let us try to read the numbers. Okay, that's just a visual validation that whatever we did, it actually worked. Okay, we have applied two transformations. One was a simple scaling, and then we applied a rotation along with it. Okay, and we came up with an answer. Alright, so what is the big deal really? I mean, we could have applied the same thing that we learned in coordinate geometry, that you could individually apply the scaling formula that we got over here, and then the rotate formula, because we learned them there. Okay, why make life much more difficult by introducing matrices here? The reason being is that if you just think about those two operations, the scaling and rotation, what we did here is we came from the left side, we did all this multiplication, and we got this matrix now. And if you look at the point P, it really means a point on the earth, right? Point on the surface of the earth. And if you go back, you'll see that there are a lot more points. It's just not this point over here. It can be any of these points. So whatever point it is, let me pick up one such point over here. This one says 0.418, 0.271, and 0.277. Okay, so let's say we got a new point. Our entire transformation is much simpler now because we can plug in those numbers over here. These three numbers will be replaced by whatever coordinates we read on the surface of the earth. Plug those numbers in, carry out the multiplication again, and we get the same, well, not the same, but the proper answer right away. We do not have to do scaling, we do not have to do rotation anymore, because all those things are combined into one thing. So if you went like coordinate geometry style, you'd have to do the scaling individually for each and every point. You'd have to individually rotate them. Now we don't have to do it anymore because we have this one matrix that takes care of both the tasks, and you can simply multiply it with the new point. So if you have 1 million points on the polygon mesh, it doesn't really matter. You have to do this operation on all 1 million of them, but it's one operation. But in our coordinate geometry style, what you'd have to do, you'd have to carry out each and every individual operation separately, and the results will depend on each of those steps. And that will slow down the entire process. In computer graphics, it's a big problem. If you slow down the process of animation, things will get choppy. I mean, you'll see one frame, there will be a delay, and you'll see the next frame after a delay, and then there will be another delay. So you have to save time as much as possible. And here is one very good technique of how you can save time by combining all these things together. Okay. And more importantly, nowadays what we do, well, not really nowadays, I mean, we have been doing that for a long time, that we manufacture the graphics card in such a way that it can perform matrix multiplications really fast. There is particular hardware implemented over there that takes care of the matrix multiplications. Okay. And when we call functions from our program, you'll also see that we deal with matrices only. We define matrices for each of these things. Okay, we call, say, rotate, translate, and that really means that we put down a matrix one after another. All right. All right, so where are we going with all these things? We have already defined two transformations, two affine transformations, the scale and rotate in matrix form. So the only one left is the translate, right? If we can bring that in, then we're done with the whole thing. We will be able to rotate, translate, and scale the whole thing in one go. So before we get there, let me just pass this attendance sheet to you. date is today? March 28th. So we got two classes today, right? Back-to-back two classes. I think we'll be done a lot earlier today if we just continue like this. I don't want to take two full classes. Well, maybe one class and a half. All right, so if you all agree, I mean, we will just carry on. Or if you need a break, I mean, that's fine too. I don't know, I'll let you guys go early a bit. Okay, so you saw the pattern, right? That we take the formulas that we had from coordinate geometry and then we just put it in matrix form. So that's exactly what we're going to do, but we are going to do it for translate. Right? So let us copy this. This is our translate, and that's probably the easiest transformation to understand. I simply want to write a formula that works for translate. Okay, so just like before, we will have our point, this px, y, and pz. Alright, let us write it down. We got a point P, we have the coordinates x, y, and z. Okay, this is one matrix, and after the transformation, the resultant matrix will be just P prime. We're going to get x prime, y prime, and z prime. So what you can imagine already that we need a 3x3 matrix over here that will do the transformation, and over here this is actually the translate, and let's say the translate will be by amount of tx, ty, and tz. Is that clear? Okay, so we have the same thing, tx, ty, and tz right here. Okay. So help me out with the entries. How do you write this? How do you write the, let's say, the first row, so that you multiply it with x, y, and z to come up with x plus tx? I mean, the second and third entry is very easy to see because you can already see that there is no y and z. There is no y and z over here. And we just need to put in something over here so that we get x plus tx. What are you suggesting? Tx? Well, that doesn't work because if you put that, you get x times tx. what do we have? X plus Tx. 1 plus Tx. One plus T. There is nothing called T over here. Well, if you even try this thing, 1 plus Tx, what you get as output is X plus. That's not what we wanted, right? What's that? No.
1 plus Tx by X.
Yeah, we're getting somewhere. I mean, let me answer Shev's question first. If you do that, then it doesn't work because we get X all right, but we get YTx. So it has to be 0. And Ibrahim's answer should do for now. And that's the only possible answer over here, which is a really bad answer. It works, but it also doesn't work. Alright, it serves the purpose, as far as this point, that you get this x prime equal to x plus tx. This is fine, and that's exactly what we needed, right? So for y prime, you can imagine that we would put in 0, 1 plus ty by y, and finally 0 for the third entry, and then we'd have 0, 0, 1 plus tz by z, okay? Why is this a problem?
X can be 0.
X can be 0, yes, X can be 0, and that's a problem, yes, because you can get division by 0 here, okay? So you should never want a division by 0 anywhere in your formula, or the scope of it. So, but that's not the real problem. You see, the way we have set up the previous example, I mean, we can come up with a matrix like this and multiply any point on the mesh with that matrix. There is no dependence of this matrix with this point. Are they related in any way? No. You can totally separate out the operation that you're going to perform, the transformation that you're going to perform, if you can keep it separate and take each and every point and then multiply with it. The way we have this translate over here, it's no longer solvable, right? There is a direct dependence on the point itself. So if you don't know the x value that you're going to translate, you cannot use this matrix. Okay? It is fine to ask for how much you're going to translate to write this matrix. Okay? But you cannot ask for the actual coordinate of the x value. If you do so, then these two matrices will be dependent on each other. Well, actually not each other. This matrix will be dependent on the point itself, P. And that's a bad thing. You want total independence over here because you want to multiply all these transformation matrices to come up with one transformation matrix that you're going to multiply with all the points. But if you have a dependence like this, it's no longer possible. So, what's the answer? How can we write a 3 by 3 matrix that does exactly this thing and that also doesn't have any dependence on the point itself? How do we do it? We don't do it because it's not possible. Right? So all that talk about writing a matrix that works like this goes out of the window because it's not possible at all. That's the first realization. Then what we do is, if you can't solve a problem, you redefine it, right? The problem that we had is, what was the problem itself? That find a 3 by 3 transformation matrix that does the translate and doesn't depend on the point itself. Okay? So we're going to try again. Alright? And this is where we redefine the problem itself. Let's say that the point that we had was not a 3 by 1 point. Okay, we know about 1D points. We also have dealt a lot with 2D Cartesian coordinate system. In computer graphics, we're dealing with a lot of 3D Cartesian coordinate system. So let us just take it one step higher. We're going into 4D. Alright, so over here there will be something, right? And that for now, let us put in a label W, alright? And for our case, if you're not worried about this thing, we can simply plug in 0. So if you have a 4 by 1 matrix over here and you want another 4 by 1 matrix as output, what do? You multiply it with a 4 by 4, right? Okay. So see what we do over here. We want, what was it? X plus tx, right? We put 1 over here so that we get x. We put 0 over here so that we don't get any y. We put 0 over here so that we do not get any z. And for w, to keep ourselves, make things easy for us, we'll put in 1. And here we can simply throw in does that work now? If you had a coordinate system that takes a 4th parameter, okay, a point has 4 coordinates, not 3 coordinates, and the 4th coordinate is just a simple 1. So try it out now. X prime is equal to x plus 0y plus 0z plus tx. Tx times 1, right? Can we try the second thing over here? 0, 1, and then 0, 0, 1, and then what happens to this 1 now? Well, you got to make sure that all these transformations leaves the last coordinate as 1. You don't want to ruin that, right? So that's why we would put in 0, 0, 0, and 1, so that 1 gets multiplied with 1 and stays like that. Okay? Because it's going to be a basis of all of their transformations, and that's why we leave it as 0, 0, 0, and 1 over here, and finally that gives you the formula for translation, like so, and you get a 4 by 1 as output, just like that. Is that clear? Alright, so see what we got over here is that we have a 4 by 4 translation matrix, and if you're going to chain this, that was the root of our discussion, that how do we solve this problem of the Earth orbiting around the sun, but at the same time rotating on its own axis. See, we scale first, then we rotate, then we translate, right? And what was our idea? That we take all these 4 operations, do the matrix multiplication first, and come up with a single matrix, right? So for rotation, we got a 3 by 3 matrix. For translation, what do we have? 4 by 4 matrix, does it work? It doesn't work. I mean, you stop right there because you cannot do the matrix multiplication. You cannot multiply a 3 by 3 matrix with a 4 by 4 matrix. So that's again a problem, right? Everything that we talked about in terms of coming up with matrices, they don't work anymore. Because we now have a 4 by 4 matrix for translation, it works. We have a 3 by 3 matrix for rotation and scaling, they also work, but together they don't work, right? So we have to come down to the same concept somehow. And that's why we have to rewrite our formula for scale and rotate. Okay? So you cannot squeeze down a 4 by 4 into a 3 by 3, but you can certainly expand a 3 by 3 matrix into a 4 by 4. That's what we're going to do. So I'm going to take this thing because I don't want to rewrite the whole thing again. Right, so let us take this one and we'll have a formula for scale. Let me move it down a bit. Alright, so we only need to change this bit. We only need to change this bit because the last row is for the very last entry, which should remain as 1, right? And help me out over here. How can you write 4 numbers so that the end result is x prime equal to sx times x? That's the formula for scale. What was it? Sx times x, 0 times y, 0 times z, 0 times 1, so that it gets cancelled out. And if you can write down the first row, well, it's kind of obvious what you do for the remaining rows, right? What would that be?
0, xy,
and then?
0,
so kind of easy, right? No big deal. So this is our translate matrix. This is our scale matrix. And now finally we need to write the rotate matrix. We had a 3 by 3 version before. We only need to write a 4 by 4 for it. So let me see if I can copy from here, or I can actually just write a new one. Okay, so this rotate, right, about the z-axis, and we're going to rotate by some theta degrees. What should be the entries? I mean, this last one is kind of obvious, this last row, so let us take it out. We need to make sure that we have x cos theta minus y sin theta, and there is no z, right? So that's a big clue right there. Minus, this is the second row, where I kind of need to expand this. Let me do that first. Cos theta, sine theta, and 0, right? Cos theta minus sine theta and 0. What we got over here? Sine theta, cos theta, 0. And 0, 0, 1, because z needs to be z itself. And this is 0, 0, 0, 1. So it's a very simple setup that we have. We got the translate, scale, and rotate all written down as 4 by 4 matrices. And how does that help? Now everything is in the same base right now. We have all 4 by 4 matrices. We can do our pre-computation. We can multiply all these things together to come up with one matrix. And whatever many points we have on the polygon mesh doesn't matter anymore. We apply the same matrix on each and every one of them to get the final output. Alright? And since this is implemented at the hardware level, it will work really fast. So we have advantage over there as well. Alright, so as far as the final exam goes, I mean, in some semesters I had this topic covered in midterms when we had 2 midterms. You may find a long description of a setup, of a lot of rotations happening, a lot of scaling happening, and you need to come up with a construction like this. Where we will have a point, we will have a chain of matrices, and that will give us our final answer. Okay. Let me see if I can find any one of these, because that's easier to explain than. I have them downloaded already. Question number 4. Let us take a bit of time to read that and see if we can relate this. try to help over here. This is probably easier understood if you if you have some figure over here to help you out. All right. So first of all, to keep things simple, we have a plane, right? This is the plane that the motorbike is running on. Let us imagine that this is our road, right? And to make it look more like road, I will just squeeze it on the y-axis. So let us imagine that this is our road. What we know over here is that the road is at, well, this is Z over here, but let us imagine that this is actually y-axis, just for convenience, all right? And this is the x-axis, because this is in 2D. This whole thing is written in 2D format. But you can apply 3D stuff over here. There is no talk about Z anywhere. Okay, so we got a road over here, and what we have are two circles for two wheels, right? So let us imagine that we have one over here, and one over here. So this is our motorbike, right? Yes, it doesn't look like a motorbike, but that's okay, I guess, for now. What we do have is, let's say they form, well, let us make it a motorbike, right? So let us imagine that there is a handle, and we got a mudguard like this, and a seat over here. Yeah, still doesn't look like a motorbike, but I mean, that would do, right, for now. Okay, so the center of gravity is somewhere over here, right at the origin, it says. And these things are W units apart from the center. And the radius of the two wheels are R, and also we have y equal to minus r as a plane that defines the road. Is this construction clear? So what happens over here is that this front wheel and the back wheel, they rotate, right? That's how the motorcycle runs forward. They have to rotate at a certain speed so that we can have the speed as s kilometers per hour. Okay? So if we were pushing a cart, then it's easy to say that what s kilometer per hour means, because you're going to move s kilometers in 1 hour, right? But right now we got two wheels and they are circular objects. In order to move s kilometer per hour, how do you calculate what's going to be the angular velocity on the wheels? So you need to understand one thing, that when we say it goes s kilometer per hour in a particular direction, that's the direction. You don't know right now is how fast these wheels are moving, but you can certainly calculate that. The question is how. What's that? We need the circumference, right? We need the circumference of the wheels. So, just think about it in real life. If you have very long wheels, right? I mean, very big wheels with a huge radius, you can move a lot faster because every time you move this whole thing, one unit, you're going to go for a long distance versus if you have really small wheels, they need to rotate a lot more times to travel the same distance, right? So first of all, we need to know what's the circumference of one wheel. And that's easy to compute. It's 2 pi r. In 1 hour, we travel what distance? Is kilometer. So in the same 1 hour, how many times this wheel needs to rotate? Is divided by 2 pi r. That many times we need to rotate, right? Let me go for a new page. And let me write this down. We need to alright, so we need to rotate 2 pi r is divided by 2 pi r times in 1 hour. Can we say this? Because that's the distance we need to travel. Can we say this? Because in one full rotation, we're actually rotating 360 degrees. So that means we're going to rotate s divided by 2 pi r into 360 degrees in 1 hour. All right, if you look at the question now, we want to find out the location of point P and Q at any given time in t seconds, right? But this is given in 1 hour, so we can copy this and say that this is in 1 hour. If you turn it into seconds, what happens then? If you have to divide it by, in 1 hour there are 60 minutes, and in 1 minute there are 60 seconds. Equal to that many degrees in 1 second. Alright, so if you're given in t seconds, then that means that you have to multiply with a t. Okay, so that's how you can find out how many degrees you need to rotate within that given time. Is that clear? So for that bit, well, there was no computer graphics involved. It was mostly physics and some math right there. Okay, so once you have that part done, right, we know how much we need to rotate, and then we need to find out the location of this point and see how it goes. All right. So this is where I'm going to ask you to write it down. Like, think of this problem in multiple pieces. First of all, let us keep things very simple. Let us imagine that the point was right at the origin. Let us talk about this point right here. Okay. if this point was on the origin, what's the first thing you do? You move it out by R unit so that it can rotate like this. Well, more like this actually. So if you move it move it from the origin a bit, then start rotating, it's going to move like this. Alright, so translate first. By how much? R. So the point itself is initially 0, 0, 0. Then you translate that along the x-axis by R unit. Then you rotate it. Rotate it by how many degrees? By this thing. By that many degrees. In your matrix, there will be a number like this, which is dependent on a parameter t, because that's what's written in the question, because you're going to plug in a number t and then you'll get the total rotation from there. You can simplify this bit, okay, but write it in terms of s and t, whatever it is, you're going to get the values. Now, it's not the end though. You need to move it out, right? You need to move it out on the x-axis some more. By how much? By w. So there is another translate. So you get the front wheel like that. And it's going to translate and it's going to sit right there. So if you plug in the value of t, then we will have an animation where we see that the front wheel is rotating like that. Hello. Sorry about that. Okay. So we can keep on rotating like this, and we also moved it out by W units, so it's going to sit right there and it's going to keep on rotating. But that's not how a motorbike works. When you say that it runs s kilometer per hour, it's going to move forward. It's going to travel s kilometer in an hour. Okay? What we have in the question is in terms of seconds. So if it travels s kilometer in 1 hour, how much does it travel in 1 second? S divided by 3600. How much does it travel in t seconds? This whole thing, s divided by 3600 times t. That's the amount. It's going to move forward in the x direction in t seconds. So that's again another translate. Okay, so let us try to summarize this. What's our point? The point is, let's say, right at the origin, it's 0, 0, 0. The first operation is going to be translate by R unit along the x-axis. Then R. R is the radius, so it needs to rotate like that. Okay. We're going to, well, let me show you over here. So right now it's right here and it's going to rotate like this. That's the first rotation I want to do, and then after this I'm going to move it by W units. That's why. Okay. So yeah, I think it's easier to write it down over here and easier to follow. So initially we have a point. This is 0, 0, 0, 1. We have to write it in 4D, right? We take this point, we translate it by R00. That's a translate, right? We will have a matrix over here, and I'm going to ask you to write it down by yourself. You know what it means, right? Can we write TR00? Can we write this matrix? Yes? No? Okay. right? So that's one multiplication over here. Then what we do, we rotate it at a certain speed. And in order to write that, it's going to be a rotate against the z-axis, because x and y will change, z will not change over here. And that's going to be, in terms of theta, what's the theta? It's going to be s divided by two pi r into 360 divided by 3600. I mean, this part can be simplified a lot. You have to carry out all these calculations. I mean, 360 divided by 3600, this is 1/10 already, and this is going to be 1/20th. And then we multiply this by t. So that's the rotation, right? And after this rotate, you need to move this front wheel. If it's the front wheel, you need to translate that by w it is on the x-axis. That's why this is 0, 0. And after this translate, I mean, things will be in place, but we need to move it forward at a certain speed. So again, we need another translate, and that's going to be how much? We move s kilometer per hour, so s divided by 3600 times t, because we're talking about t seconds. And that's what it is. So if you could write it in terms of matrices, I didn't write the matrices over here, but in your exam paper you have to fill in the details of the matrix. Carrying out the matrix multiplication is not so important. I may ask for it, I may not ask for it, but I'm not going to give you much mark for the multiplication itself. It's mostly about setting it up in the proper order, because that's what is really important. Anyone can do the matrix multiplication. So that's for the front wheel. For the back wheel, it's pretty much the same setup. It's just that instead of W over here, we will have minus W. So that's what the question boils down to. And if you look through the other questions of previous semesters, you'd see there is one such question over there in terms of matrices. Sometimes it's about motorbikes, sometimes it's about an ant moving on a cylinder or something as such. Okay. So there will be some interesting problem where you have to come up with some sort of matrix multiplication setup like so. Okay. Did we understand this? How we got this thing? Okay, all right. Let us try this. We are traveling s kilometer per hour, right? Okay. In one full rotation, we travel how much? That's 2 pi r. That's the distance we travel, right? And let us imagine, I mean, I should have been specific about it, but let us imagine that r is defined in terms of kilometer. I mean, there has to be some unit given. So there was a mistake in this question itself. I didn't specify that. Either r is measured in meters or kilometers or whatever unit that is, it has to be specified. So let us just imagine that we travel that much kilometer. So that means we do how many full rotations in 1 hour? We do s divided by 2 pi r. In one rotation we go, let's say 10 meters, right? And in 1 hour we go 1,000 meters. So that would mean that we do this thing 100 times. That would mean that you would have 100 full rotations. Okay, so that's the first thing. So this is in 1 hour. How much do you rotate in 1 second? Divided by 3600. How much do you rotate in t seconds? Multiplied by t. That's how you come up with that. It's about taking a circle, flattening it out, and if you do that, if it has r radius, if you flatten it out, you get 2 pi r. Any other question about this one? It wasn't really a simple one, this question. Okay, but have a look at the other questions that would give you some clue. This is from 2016, but I've uploaded questions from many other semesters, so you can go through them and have a look at those. And if you don't understand any of those questions, feel free to bring them up in class so that we can discuss those things. Okay. All right. What else? So we had a Blender assignment, right? The car assignment, it's already submitted, and right now we are working on animation. We have a very crude figure. Alright, so we have a very crude figure over here. This monkey does like this, and what I want you guys to do, this is going to be your 1, 2, 3, the third assignment, right? So we have submitted 2 Blender assignments already. The third Blender assignment is going to be about animation and a little bit of modeling. So you will come up with a robot that looks like this, or actually much better than that. You need to have legs on it, because the task that I'm going to give you will involve some legs. Right? We know how to build this, or a much better robot than this one, right? Build your robot with some character. I mean, whatever body parts you're going to bring in, do that. The modeling is not so important over here, but try to make it a bit realistic if you'd like, right? The task itself, let me write this down first. Rigging means creating the armature from a single bone. You create multiple bones. I've showed that in a previous class. That's how the robot works, right? That we have one bone, we extruded multiple bones out of it, and then we parented that. You can watch the video, or if you didn't understand something over there, I can repeat that. If you need that, let me know in the next class, or even now. Right? So once you have this set up, you have to attach different mesh parts that we have along with each and every one of these objects. Then the rest is simple. We do a keyframe animation, so you insert keyframes one after another. The only thing left over here is this moonwalk thing. How many of us know the moonwalk? We know that? Alright, okay. At least some of us do. Hasan Tariq sir had a dream that he'd make Rakib sir do a moonwalk in the picnic. It didn't really happen. So for those of you who don't know what a moonwalk is, let me just show you right now. Alright, so I think that's a big collection, alright. So I'm not going to play the whole thing. That right there is the moonwalk. So you don't have to do the full dance, obviously. I mean, you don't have to do any dance. If you want to, I mean, that's up to you. Your robot has to do this moonwalk, right? So that's the first step. And later on, we'll bring in real human character. You can build a 3D model of yourself or anyone you'd like, and then we'll do some animation over there. Okay. So is the task clear? All right. Make sure that your robot has all the limbs, like it has the legs, different parts of the legs. It should also have the feet because it has a lot of focus on the feet itself. You have to make it multi-part. All right. And also you need arms, you need the head. So you can use the monkey head, that's not a problem. But make sure that your robot moves in a realistic way, like this. And also, it slides on the floor, like so. Okay? So with that said, I think the topics that I wanted to cover for today's class is done. And leave me this as a reference. Okay. Oh, we need to set up a due date for this. This one is rather simple. I mean, it's not an intricate model. You don't have to bring in a lot of details. You need some time for modeling, but the main part would be about rigging it right and also then animating that. So help me out. What should be your deadline for this? Today is March 28th. How about April 4th, a week from now? Too soon? I mean, I don't know how busy you are or how free you are or how much time it takes for you, so you're the best judge of it. How many of you have a problem if I set it on April 4th? No problem from anyone? Seventh? Then you get the Thursday and Friday, and the entire Saturday. Although it doesn't make any difference, right? Because we got classes on Fridays, at least some of us do. So what about 7th? Is that okay? I can push it to 10th, not a big deal, but then we'll have some more assignments. I mean, this is only the third one. I wanted to go for 5 or 6 for blenders. Okay, then 7th. Okay, any question or on anything that we talked about today? No? Alright, so I'm going to finish this off right now then.